Hello, everyone. Thank you very much for joining this presentation. My name is Shuhei Matsumoto. I'm a software engineer at NVIDIA and one of the core maintainers in the SPDK project. There are two topics in this presentation. The first part, I will talk about NVMe Multipath and I/O error resiliency. In the second part, Mike Gertz, principal engineer at NVIDIA, will talk about the external snapshot feature. Let's start the first part, SPDK NVMe Multipath and I/O error resiliency. This is the agenda of my part. I/O error resiliency is variable itself, even if we do not use multipath. On the other hand, I/O error resiliency is critical for multipath. Hence, we developed and supported these two features simultaneously. The first three topics, path error recovery, I/O retry, and I/O timeout, are about I/O error resiliency. The next five topics, multipath mode, create multipath, I/O channel for multipath, path selection policy, and asymmetric namespace access handling are about multipath. Then I will explain the basic usage, and finally, I share one reference setting for I/O error resiliency. I talk about path error recovery first. Before SPDK v22.01, path error recovery was synchronous and not controlled. It occupied CPU until it succeeded. Since SPDK v22.01, SPDK does not have such limitation anymore. If the NVMe driver detects an error on a queue pair, it disconnects the queue pair and notifies the error to the NVMe bdev module. Then the NVMe bdev module starts resetting the corresponding controller. The controller reset sequence consists of the following 5 steps. First, disconnect and delete all I/O queue pairs. Second, disconnect admin queue pair. Third, connect admin queue pair. Fourth, configure the controller. Fifth, create and connect all I/O queue pairs. If the step 3, 4, or 5 fails, the reset sequence reverts to the step 3, and then it is retried after reconnect delay seconds. Then, if the controller is not recovered within controller loss timeout seconds, it is deleted automatically. If controller loss timeout sec is -1, it retries indefinitely. Many codes are rewritten and all disconnect and connect operations are done asynchronously now. Hence, CPU is not occupied even if controller is down. The last bullet is tips. By default, error detection on a queue pair is very slow for TCP and RDMA transports. For fast error detection, a global option, transport ACK timeout, is very useful. This page is about I/O retry. I/O retry is critically necessary for some use cases because the upper layer may not accept any I/O error, and any I/O error may result in system down. Hence, we supported I/O retry. There is a global option with retry count to control the number of retries when an I/O is returned with error. Each I/O has a retry count and a timer to schedule an I/O retry. If the retry count of an I/O is less than the bdev retry count, the failed I/O is allowed to retry and the retry count is incremented. The timer of an I/O is used to schedule an I/O retry at a particular time in the future. Each I/O channel for a bdev has a sorted I/O retry list and an I/O retry poller. Retried I/Os are inserted into the I/O retry list. The I/O retry poller is scheduled to the closest expiration. If there is no retried I/O, the I/O retry poller is stopped. If an I/O is returned with error, the I/O completion handler executes the following steps. First, if the do not retry bit is set or the retry count exceeds the limit, complete the I/O with the returned error. If the error is a pass error, insert the I/O to the I/O retry list with no delay. Third, if the error is an I/O error, insert the I/O to the I/O retry list with the delay reported by the command retry delay. When submitting or retrying an I/O, there may be no available I/O path. However, if there is any I/O path which is recovering, insert the I/O to the I/O retry list with 1 second delay. This may result in indefinite I/O queuing. To avoid such indefinite queuing, there is a per controller option, fast I/O fail timeout sec. If the controller is not recovered within fast I/O fail timeout sec seconds, I/Os are not queued but returned with an I/O error to the upper layer. The NVMe driver supports I/O timeout for submitted I/Os. The NVMe bdev module provides 3 actions for I/O timeout: abort, reset, or none. Users can choose one of the actions as a global option, action on timeout. Users can set different timeout values for I/O commands and admin commands by 2 global options, timeout US and timeout admin US. If the action is abort, try aborting the timeout I/O, and if it failed, the recovery is escalated to the controller reset. If the action is reset, start the controller reset from first. If the action is none, just collect error log and do nothing. On the next page, I will talk about the multipath topics. Now SPDK NVMe bdev module has 3 modes. The first mode is multipath. SPDK v22.01 newly supported NVMe multipath on the initiator side. SPDK's NVMe multipath provides high performance and the same functionalities as the Linux kernel native NVMe multipath. In this mode, active connections are maintained for every path and used based on a policy of either active-passive or active-active. The multipath also supports asymmetric namespace access NA and uses NA for path selections. The merge path is transport protocol independent. Heterogeneous merge path configuration, for example, TCP and RDMA, is supported. The second mode is failover. Failover has been supported since SPDK v20.10. In the failover mode, only one active connection is maintained, and one alternate path is connected only during the switchover. This reduces the number of active connections at any given time. However, it leads to slow switchover. The third mode is disable. Some users do not want to use merge path or failover. The disabled mode is provided for such users. In this mode, each path is maintained independently. In this page, I talk about how to create merge path configuration. A user can establish connections on multiple independent paths to the same subsystem for bdevs by calling the bdev NVMe attach controller RPC multiple times with the same bdev controller name. Additionally, the merge path parameter for the RPC must be set to merge path when connecting the second or later passes. For each path, a few steps are executed. First, create a controller. Then discover the set of namespaces presented by that controller. For each found namespace, we attempt to match it with an existing bdev. If a bdev is found, we add the given namespace to the bdev as an alternate path. If no bdev is found, we create a new bdev. The diagram in this page shows the image of one simple merge path configuration. I/O channel is a fundamental abstraction in SPDK to submit I/O without taking any locks. In this page, I talk about some enhancements for I/O channel to support merge paths. For each SPDK thread, we create an I/O channel for bdev and provide it to the upper layer. I/O channel for the bdev has an I/O path for each namespace. We do not find the I/O path in the left diagram for supporting merge path. I/O path is a new abstraction to submit I/O to an I/O path among multiple I/O paths. I/O path consists of pointers to a namespace and an I/O channel for a controller. I/O channel for a controller has an I/O queue pair as its dynamic context. I/O channel for a controller is shared by multiple I/O paths if the controller has multiple namespaces. Based on the I/O channel I talked in the last page, I/O path to submit I/O is selected by either one of active passive or active active. For active passive, each I/O channel for bdev has a cache to store the first found optimal I/O path and use it for I/O submission. Users can specify the preferred I/O path manually if they want. Users can dynamically set the preferred I/O path using the bdev NVMe set preferred path RPC. Such assignment is realized naturally by moving the I/O path to the head of the I/O path list. By default, if the preferred path is restored, playback to it is done automatically. The automatic static failback can be disabled by a global option, disable auto failback. If the auto failback is disabled, the bdev NVMe set preferred path RPC can be used to do manual failback. Another policy is active-active. Currently, the active-active policy uses the round-robin algorithm and submits an I/O to each I/O path in circular order. More path selection algorithms will be added to the active-active policy in the future. This page is about asymmetric namespace access (ANA) handling. ANA is an NVMe standard to inform an initiator of the most optimal way to access a given namespace. ANA is synonymous with SCSI allure. If an I/O is returned with an ANA error or an ANA change notice event is received, the ANA state may be changed. In this case, read the ANA log page to check the ANA state changes. Only ANA optimal I/O paths are used unless non-ANA optimal path is available. If an I/O path is in ANA transition, that is, its namespace reports the ANA inaccessible state or the ANA change state, we queue I/Os to wait until the namespace becomes accessible again. The ANA transition should end within the ANA transition time seconds. However, if the namespace does not become accessible, that is, does not report the ANA optimized state or the ANA accessible state within the ANA transition time seconds, queued I/Os are returned with error barrier. I talk about basic usage of multipath and I/O error resiliency in this page. The first bullet is to attach two controllers and aggregate these into a single bdev controller NVMe 0 by using the RPC bdev NVMe attach controller. If these two controllers have a shared namespace whose namespace ID is 1, a single NVMe bdev NVMe 0 and 1 is created. For the NVMe bdev module, the default value of bdev retry count is 3 and I/O retry is enabled by default. Controller loss timeout sec is set to -1 and the reconnect delay sec is set to 20. Hence, controller reconnect will be retried once per 20 seconds until it succeeds. Move to the second bullet. To confirm if multipath is configured correctly, two RPCs bdev get bdevs and bdev NVMe get controllers are available. Move to the third bullet. To monitor the current multipath state, an RPC bdev NVMe get I/O paths are available. The last page is a table for reference settings for I/O error resiliency. This is a result of our discussion in our team. You can decide the settings by your own requirement, but please use this table to design the setting if usable. Thank you so much for your kind attention. It's your turn, Mike. Please go ahead.
Thank you, Shuhei. I'm going to talk about SPDK external snapshots. I'm Mike Gertz from NVIDIA. External snapshots allow a volume manager to use a read-only device that is external to the volume manager as a snapshot. The same concept that I'm discussing today is present in the Linux device mapper. I'm developing external snapshots for SPDK using the SPDK lvstore and blobstore. This will allow any read-only bdev to be used as the snapshot for lvol clones. A key use case for this is to provide instant read-write ephemeral clones of remote disk images. A read-only base image can reside on shared storage and be used by VMs on an arbitrary number of hosts. Writes can then be kept local to where SPDK runs, which is likely co-located with the VMs. I often use the term eSnap clone as a shorter way to say clone of an external snapshot. The SPDK lvstore is a thin veneer over the blobstore, and as such, almost all the I/O path changes are in the blobstore. The lvstore changes focus on things like eSnap clone creation and opening eSnaps on behalf of the blobstore. This is a somewhat straightforward adaptation of the existing support for thin provisioning and clones. The key change is the introduction of a new way to create and use custom blobstore devices as the bdev. With thin provisioning, the bdev is a zeros device, which just fills the buffer with zeros when read. With traditional clones, the bdev is a blobdev, which is able to satisfy reads from any blob in the same blobstore. My work allows the blobstore consumer to provide a callback that will allocate a blob bdev and register with the blob as the blob's bdev. In the case of lvstore, any bdev can be used as the external snapshot. The interface is flexible such that an external snapshot does not need to use a bdev. Unit tests have been written that leverage this flexibility so that eSnap clones can be tested without introducing a dependency on bdevs. When a blobstore consumer needs an I/O channel, it calls SPDK BS alloc I/O channel. This returns an SPDK BS channel which stores the dev channel required to perform I/O on the device that contains the blobstore. This dev channel is only useful for performing I/O on the one device. In order to read from external snapshots, a channel per external snapshot or eSnap clone is required. To keep track of these external snapshot channels, a tree has been added to SPDK BS channel. This eSnap channels tree is lazily populated. A channel for the external snapshot device is added on the first read. Reads from the bdev always occur through BS batch or BS sequence read or readv functions. The allocation of BS batch and BS sequence have been updated to populate the SPDK BS request set's new back channel field to contain the SPDK I/O channel that these read and readv functions should use to read from the back bsdev. With the normal clone, the back channel is the SPDK I/O channel associated with the BS channel. With an eSnap clone, the back channel is the SPDK I/O channel associated with the external snapshot bsdev. An eSnap clone can be recognized by an internal xadder, an invalid flag, and its parent ID. These exist in memory and on disk. The metadata stored by blob eSnap ID is opaque to the blobstore, but needs to be meaningful to the blobstore consumer. lvstore uses the eSnap's UUID as the eSnap ID. Many bdev types do not support setting the UUID, so some work will be needed to improve that, or we will need to provide a way for lvstore to opt into using bdev names. The SPDK blob eSnap invalid flag prevents blob stores that don't support eSnap clones from trying to load this blob. The SPDK blob ID eSnap parent ID is used during snapshot and inflate operations to indicate that special handling is needed. To create an eSnap clone, SPDK blob create is called with two new fields populated. The eSnap ID is an opaque value that gets stored in a blobstore internal xadder. As the blob is being loaded, the blobstore's eSnap bsdev create function is called. If the blobstore was opened without specifying the eSnap bsdev create function, the blob will fail to load. As mentioned in the previous slide, the eSnap bsdev create function is needed to tell the blobstore how to ask the consumer to create blobstore devices for the external snapshot. A pointer to the external bsdev create function is stored in the blobstore's in-memory configuration until the blobstore is unloaded. The blobstore may also store a context pointer that is passed with each call to esnap bsdev create. The esnap bsdev create function will typically retrieve an identifier and use it in the creation of a bsdev that it passes back to the blobstore via the supplied callback. The code on the left side of this slide is from blobstore.h and blobstore.c. The code on the right is from lvol.c. As you'll gather from the previous slide, this one, lvs esnap dev create is called when the lvstore loads a blob. Almost everything I've talked about up until now happens in the blobstore. The lvstore gets new methods creating esnap clones and viewing information about them. In particular, SPDK lvol create bdev clone can be used to create an esnap clone of a bdev. This can be called directly or via the bdev lvol clone bdev RPC call. Configuration and state information that is related to external snapshots can be seen in the driver specific section of the objects returned from bdev get bdevs. When the lvstore creates an esnap clone, it needs the bdev that accesses the external snapshot to be read-only so long as it is in use. Since there are many clones of the same external snapshot, since there may be many clones of the same external snapshot, there is a need to claim the bdev multiple times. Historically, claims have catered to the exclusive writer use case and have not cared about whether there are other writers when the claim is taken. To support external snapshots, I'm introducing an improved bdev claims interface that introduces a stricter form of claims like we have today, as well as shared read-only and shared read-write claims. Each of these version 2 claims is associated with a bdev descriptor and is released when the descriptor is closed. An lvstore is typically loaded via vbdev lvol's examine disk callback. The examine disk callback is called as the bdev containing the lvstore is registered. The loading of the lvstore could be at a time when the bdevs that are used as external snapshots do not exist. They may be missing due to the order that the devices are added to SPDK at startup, due to an offline remote target, or perhaps other reasons. As you may recall, as an esnap clone blob is being loaded, it calls lvs esnap dev create. If lvs esnap dev create cannot find the required bdev, it adds it to a per lvstore tree of missing bdevs. As new bdevs are registered, the vbdev lvol examine config callback checks each lvstore's missing bdevs tree to see if the newly registered bdev is needed by any lvols. If the bdev is needed, the examine config callback will take a read-only many claim on the bdev and trigger the required updates on the affected lvols. These updates create a new blob bdev and ask the blob to replace its back bsdev with this new blob bdev. While an external snapshot is missing, the lvol that is a clone of the missing esnap will be open and able to service I/O that does not involve the external snapshots. That is, reads and writes that access only clusters that are allocated in the blobstore will not be affected. Any attempt to read from the missing external snapshot will result in an I/O error. While this obviously affects reads, it will also affect writes that trigger a copy on write that needs to read from the external snapshot. You can create external snapshot. You can create snapshots of esnap clones just like you can create a snapshot of any other blob. When a blob is snapshotted, the clusters owned by the blob are transferred to the snapshot and the original blob becomes a clone of the snapshot. This means that after creating a snapshot of an esnap clone, the snapshot itself becomes an esnap clone, and the original esnap clone is now a normal clone of the snapshot. This has an interesting effect when the clones are inflated, as I'll cover in the next few slides. Many storage systems that support clones support hydration operations. SPDK's blobstore supports two different kinds of hydration, inflate and decouple. Both of these methods remove a clone's dependence on a snapshot, meaning they will no longer be a clone. Inflate makes it so the blob's storage is fully allocated in blocks that are private to the blob. It will no longer have a back bsdev that refers to a snapshot or a zeros device. Decouple is similar, but it only removes a dependency on the snapshot. If the snapshot is then provisioned, the snapshot clusters backed by the zeros device will continue to be unallocated, implicitly zero-filled in the inflated blob. As a practical matter, inflate and decouple will usually have the same result for eSnap clones, as there is no cheap interface to ask a bdev if an LB range is all zeros. There will be a distinction if the clone has been resized to be larger than the snapshot. In the future, it may be possible to leverage the recently added seek_hole and seek_data interface to implement a hole-aware is zeros function. This diagram illustrates the trivial case of a blob being inflated. The operations that happen during the inflation are pretty much the same as the copy part of copy on write that happens during the first write to a cluster. It is safe to perform I/O on blob1 while it is being inflated. Inflating eSnap clones gets more interesting when the eSnap clones are snapshots that have been cloned. This example shows a golden image, golden1, that is an eSnap clone of an external snapshot, eSnap1. Blob1 and Blob2 are clones of golden1. Think of the left pointing arrows as the backbs dev pointer. Clones can be created and deleted as needed. If circumstances dictate that it would be best to remove the dependence on the external snapshot, golden1 can be inflated. Having golden1 between eSnap1 and the read-write blobs allows this dependency to be removed with a single data copy. Thank you very much for listening to our presentations today. We'd be happy to take your questions now.